Alright, so welcome to week 3 of advanced algorithms. This week our focus is going to be on dynamic programming, which is a really powerful paradigm for solving algorithmic problems. Maybe you have seen dynamic programming before, maybe you have not. If you have, you probably remember that dynamic programming involves a lot of recursive thinking. It involves thinking about breaking down a problem into smaller subproblems in a meaningful way, in a way that allows you to combine things to solve the problem at hand. But usually what happens if you just write down a recursive solution, which is even correct, a common issue that you will run into is that the running time blows up. So one of the things that will be a running emphasis as we discuss problems this week will be to make sure that our approaches are efficient, that we leverage something called overlapping subproblems so that we are not repeating the same computations again. So essentially what we are going to do is a lot of careful implementation of recursive ideas, and the care will basically ensure that we have nice, speedy algorithms at the end of the day. Now, in case you have never seen dynamic programming before in an algorithms class or a data structures class, I would actually recommend going through some of the supplementary reading materials. Some of them are quite introductory, and you might want to check out some of that first, especially examples like, for instance, Fibonacci. It's a very standard introductory example, and that might be useful. So please do take a look at the course notes and look at some of the preparatory material, because as I go along, I'm going to be assuming that you've seen at least a little bit of this paradigm before. Now, I will be starting off with a problem called Longest Increasing Subsequence. And now this may be a problem that you've actually encountered before. And I would suggest that you stick around even if you're familiar with one or more solutions to this problem. And the reason for that is I'm going to use this problem as sort of a running example to introduce many of the main features of a dynamic programming based approach to a problem. So I'm going to go over my DP checklist. I'm going to highlight things that we should be watching out for. So I hope that even if the problem is not new for you, this discussion that we have will still be valuable. Now, if you want to save time, of course, you could speed up the video, or you could also go through the course notes if you feel like this is a familiar problem and you just want to get through it. So that's an alternative. So having said all that, let's get started with actually discussing longest increasing subsequence. As usual, let's set up the problem first. So what is the input? The input is going to be a sequence of numbers which we can think of as being stored in an array. So I'm going to say that we have an array A of, let's just say, integers. And the output that is expected is, as the name suggests, has something to do with the longest increasing subsequence. Now, what we will be looking for is the length of a longest increasing subsequence. Now, this is quite a bit to write down every time, so I will abbreviate this to LIS most of the time. Now, this begs the question, what is a longest increasing subsequence? So, of course, we can define this formally, but it's perhaps easier to understand it with an example. So let's do that first. So let me put down some numbers here for you. These are quite random. Alright, so here is a bunch of numbers. They are in a sequence, so don't think of it as a set. The order really matters. Okay, so this is an array of numbers, and what is a subsequence? It's basically pulling out some numbers from the original sequence in the order in which they appear. Okay, so for example, 4535 is not a subsequence because we have 45 here, but then 35 comes before it, not after it. So even though both of these numbers are present in the array, it's not considered a subsequence. Okay. Now the array could have repeated elements, so if there was another 35 sitting up front, then this would have worked. But since that's not the case in our example, this is just to emphasize what a subsequence is not. The easiest way to think about a subsequence is to say that, well, let's just go ahead and delete some of the elements in the input array, and what's left would be a valid subsequence. Okay. This is also different from what is called a substring. So there's also a notion of a substring or a subarray. You should be careful about remembering this distinction because this may come up in some other problems that you encounter either in practice or elsewhere. So a subarray is like a contiguous chunk of the given array, okay, and it's completely determined by two indices: the starting index, which let's say I temporarily denote by I, and the ending index, which I'm denoting by J. So pick two indices, potentially the same, which are between the start and the end of the array. So I'm going to index my array starting from 1. So here we have an array that has 12 elements. Then pick any pair of indices, the first, at most the second, and that will give you a subarray. So here this would be the subarray that starts at 35, includes the elements 35, 19, 87, 91, 16 and 14. It goes all the way up to there and ends at the 8th element. So that's a subarray. So the number of subarrays that you have is essentially determined by the number of ways in which you can pick these indices. So you essentially have roughly n squared subarrays, and I'll leave it as a fun exercise for you to think about how many subsequences there can be. You may have guessed that the number of subsequences that a sequence has is at least the number of substrings or subarrays that it has, because every subarray is also a valid subsequence. But there could be things that are subsequences which are not subarrays. So for example, the highlighted numbers here, which are pointing to the array indices 2, 4, 5, 7 and 9, forms a subsequence, which is not a substring or a subarray. Okay. All right. So I should say that I've used the term substring. That's usually used in the context of strings as opposed to sequences of numbers. So that was just a bit of I guess, abuse of terminology, but you get the spirit of it. I'm just trying to highlight the difference between these commonly used terms. Anyway, back to subsequences, because that's going to be the focus of our discussion. We now know what subsequences are. What is an increasing subsequence? An increasing subsequence is simply a subsequence where the elements go up, meaning they increase in value. Okay, so the highlighted subsequence here is actually not an increasing subsequence, because right in the beginning we go from 42 to 19, and already 19 is smaller than 42. So we need to get rid of 19 or 42 from the subsequence to make it a valid increasing subsequence. We also run into trouble with going from 87 to 16, and from 16 to 32 is okay, but 87 to 16 is not quite working, so let's get rid of that. 87 to 32 is also problematic, so we can get rid of 32 because that would also not be compatible with 42, so let's get rid of that. We are left with 42 followed by 87, so that's a valid increasing subsequence. Now, is it a maximal subsequence, meaning is it a subsequence where we are truly stuck at the end. Can we go no further? Well, that's not true, because we do have 91 sitting right after 87. So we could have actually extended this, and that's what we have just done. So we have 42 followed by 87 followed by 91. And given this subsequence, I don't see a way of making it any longer. If we are committed to picking these three numbers here, 42, 87, 91, there's nothing else that we can pick while maintaining that we still have a increasing subsequence. But on the other hand, is this the longest increasing subsequence? What do we mean by this? Well, the length of a subsequence is simply the number of elements in that subsequence. So the length of this one is 3. This is a subsequence of length 3. And now we want to ask ourselves, well, can we find a subsequence which has 4 elements in it? And that's actually a question to think about for a minute. This is a good place to pause the video if you would like to. But let me just point out that we have this collection of 4 elements sitting right here: 14, 32, 45, 50. That would count as a increasing subsequence which has 4 elements. So certainly the one that we had before is not the longest increasing subsequence. It's certainly being outcompeted by this other one here. But now this one, is this a longest increasing subsequence? Is there something else that has 5 elements in it? Well, I'll let you think about that, not spoil this right now, but hopefully you get the idea of what we are looking for. So we are looking for an increasing subsequence that has the largest number of elements. So given a sequence, you can write down all the increasing subsequences that it has, and next to each of these subsequences you can write down its length. And now there's going to be a set of these subsequences that have the maximum value of length, right? So any one of them would qualify as the longest increasing subsequence. Of course, some sequences may have a unique longest increasing subsequence. Some may have several. So let's see if we can come up with a quick example where there are 2 longest increasing subsequences. So here is one attempt. All right, this would actually need verification, but I do believe that, for example, we have 1, 3, 5, 9, 10. That would be one subsequence of length 5. We could also do something like 1, 2, 4, 6, and 8. Here is another subsequence of length 5. So there are at least 2 subsequences that are increasing and that have length 5. And I claim that there isn't anything that has length 6. And that's something that you can verify more or less by inspection here, or you could come back to it once we have discussed our algorithm and run this example through the algorithm just to be sure. Okay. All right, so let's actually think about now the problem of finding the length of a longest increasing subsequence. Remember, we want to think recursively, so we want to see how we can break this problem down into useful subproblems that will help us solve the main problem. So whenever we are working with sequences, a very common trick is to break it up into subproblems involving actually smaller subarrays. Okay, so let me propose here that we start with a special kind of subarray, which is sort of a suffix subarray. Okay, so let me just back up for a second and say that whenever you're dealing with an array-based problem and you want to find something in an array, like here we are trying to find the length of a longest increasing subsequence, it's pretty common to ask yourself what happens for the first I elements of the array. So this would be a prefix based subproblem. You could also ask yourself what happens for the last I elements. This would be a suffix-based subproblem. So once again, the idea is that you try to understand what the solutions would be for these smaller instances, and you'll have some sort of a base case, which is the smallest of the small instances, which can typically just be solved directly by hand. And then, just like you would do in an inductive proof, you go from the base cases and try to build up your solution all the way till the end using your recursive relationship. Okay, so that's kind of the framework of a recursive approach to solving a problem. And the other kinds of things that you could do when you're working with arrays is look for subarrays like that. So these are subarray based subproblems. Notice that here we only have n subproblems to worry about, because for every I between 1 and n there is one prefix or one suffix associated with that I. You're looking for the first element, the first two elements, the first three elements, and so on up to the first n elements, or you're looking for the last element, the second last and the last element, the third element from the end up to the end, and so on and so forth. So we have only n subproblems in such scenarios. Whereas here, just like we discussed when we were chatting about subarrays, the number of subproblems that you generate is more like n squared, right? So this would be a more expensive collection of subproblems to maintain, but if that's what you need to do, and sometimes that is what you need to do, then that's what you do, right? So let's see if we can get away with a suffix-based subproblem for LIS. Let's give that a shot. So what do I want to do here? I want to ask myself, what is the longest increasing subsequence of the last I elements? So actually, I should clarify here that when I wrote down I through n, that's the last n minus I elements, not the last I elements. So you're leaving out the first I minus 1 elements and you're looking at what happens from there. And so even what I just said might be off by 1. But again, the point is, hopefully the spirit of what we are doing is clear. Okay, so I want to focus on this suffix here. And you might ask, why are we obsessing over suffixes? Why not prefixes? And the answer is, well, I'm just going to start off by trying something. You're welcome to try prefixes as well. It's not going to be very different. The nature of the discussion that we're going to have will actually be similar. So one reason why I'm following a suffix-based approach is that that's what I already have in the notes and I want to stay consistent with that. Okay, so it's not a particularly deep reason. So let's get back to staring at the suffix here. So let's say we are looking at the array. Let me draw an array here. So what I want to focus on is this portion of the array, and I want to say, well, suppose I figured out what is the length of the LIS in this portion of the array. And if I have a systematic way to do that, then I am in business, because the final answer will simply be LIS of 1 to n, because that's just going to encompass the entire array, and that's what we are looking for. So if we could build it up from right to left, that would be great. And in terms of a base case, also we are largely sorted, because if you think about the LIS of essentially n, right? So when I is n, you're looking only at the last element. So really the longest increasing subsequence there is just one, because there's only one element to be chosen. So there's really nothing to think about here, right? The question that's interesting is, how do we build up the recurrence? So when you're thinking about recurrences, you assume that you have managed to compute the solution for all the smaller subproblems in question. Okay, so if you give me any shorter suffix of the array, right? So for example, if you want to know what is the longest increasing subsequence, or in other words, what's the length of the longest increasing subsequence for the subarray A going from j to n for any j greater than I, assume that you have this information at your fingertips. You can invoke it, you can use it in any way you want. That's the whole idea of saying that we are employing a recursive approach, right? So in particular, we know what is the length of the longest increasing subsequence of this subarray here. This information we have. And now the question is, how do we use this information to determine the length of the longest increasing subsequence of the array that we are actually interested in, which has this one extra element here? So as you can imagine, the question that we really want to ask ourselves is that, can a longest increasing subsequence from this portion be extended with this newly entered element or not? And in particular, what we want to know is there some longest increasing subsequence in that green subarray which is such that if I were to add this element to it, it would still remain an increasing subsequence? Because if it does, then that is what would qualify as a longest increasing subsequence. So just to recap what we said here, suppose we know from our recursion that the length of the longest increasing subsequence of the green array happens to be k. Okay, then notice that the longest increasing subsequence of the array, the subarray starting at I and ending at n, is going to be either k or k plus 1. Okay, it certainly cannot be more than k plus 1, because if it was more than k plus 1, then even if we knock out this element from that increasing subsequence, you would still have an increasing subsequence of length at least k plus 1 for the rest of the array, which would contradict our assumption that the length of the longest increasing subsequence in the green subarray is k. Okay, so certainly the length of any longest increasing subsequence of the entire array starting from I to n cannot be more than k plus 1. It also cannot be less than k, because we know that there is an increasing subsequence of length k in the array that starts at I plus 1, and that's a perfectly valid increasing subsequence even in the extended array, right? So we know that our answer is either k or k plus 1, but the $1 million question right now is, which one is it? Should we add 1 or should we not add 1? And what do we need to know to be able to make this decision? Like I said a moment ago, the question is there some LIS of the subarray that starts at I plus 1 and ends at n, which begins with a value that is bigger than a of I, right? Because think about it, if there is such a LIS in the green subarray, then that means that we can take that and append this fellow to it, right? Because then by adding a of I, we still maintain the increasing property of the subsequence. On the other hand, if every longest increasing subsequence of the green subarray starts at a place which is smaller than a of I, then none of them are extensible, right? So really, in that case, we know that the answer for the entire subarray starting from I all the way to n must actually be k, right? Because the only way that the answer is k plus 1 is if we can combine this guy with something that is a longest increasing subsequence. Anything shorter will not work, because if you take some shorter increasing subsequence of length at most k plus 1 and combine this with that, then you will end up with an increasing subsequence of length k itself. So you get stuck here only, right? So if you want to upgrade to level k plus 1, the only way you can do it is if you have a longest increasing subsequence in the shorter array which is compatible for expansion with the new element, okay? But notice that what did we decide to store in our DP table? We basically said that give us the length of a longest increasing subsequence from the smaller subarrays. We only asked for the length. We didn't ask for any other information about these subarrays. So with just the information about the length, notice that we are actually stuck, right? We don't have enough information to know whether we should make that upgrade or not, right? So essentially, by just storing the lengths of the LISs, we will not be able to actually push for being able to write a meaningful recurrence relation, okay? So if you say something like dp of I, so this is some sort of a DP table that I'm trying to build here, is the length of an LIS in AI to n, dp of n is 1, the answer is dp of 1, and the recurrence, let's say, is something like dp of I equals dp of I plus 1 plus 1. This is silly, right? This will not work because essentially your answer is always going to be n. And if you decide not to add the 1, then your answer is always going to be 1. And these are both going to be completely wrong most of the time, right? So really the problem is we don't know when we should add the 1 and when we should not add the 1. So to fix this, we need to go back to the drawing board and try to see if we can make our DP a little more fleshed out so that we are basically getting more information from our recurrences. Notice that this is all the information we need, right? We need to know what is the starting point of the sequence, and is the starting point large enough that I can prepend the sequence with the value that is sitting at the ith index, okay? So this is a good place for me to take a pause. What I want to do is give you some time to think about how you will fix this DP, and you can fix it in multiple ways. You can also come up with an entirely different DP that does not involve, let's say, prefixes or suffixes, but I would say take some time and think about what should you be looking for in the template of what you want to store so that you can actually write out a correct recurrence relation. And when we come back, we will talk about not one but two ways to solve the LIS problem using slightly different methods of what we want to store and how we write out the recurrences. So I'll see you then. Thanks for joining me so far.